Hello, dear students. You are welcome to Ark Institute. I am Dr. R.K. Sani, and today I am going to discuss relative acidic strength of inorganic acid as well as organic acid. And this topic is important for JEE, NEET, CSIR, JRF, UGC, etc. Okay. First, we explain relative strength of acidic and basic in aqueous solution. First, we understand some basic concept. For example, first we see about water. H2O ionize in their form H plus aqueous, or we also write H3O positive hydronium ion plus hydroxide ion aqueous. After removal of one H plus ion from the acid, the remaining part is known as conjugated base. Means OH ion is conjugated base and H2O is an acid. It is acid and it is base, conjugated base. Then when we write their ionization constant for acid, we write Ka, the concentration of H plus ion into concentration of OH ion upon molar concentration of H2O. At 298 Kelvin, the concentration of H plus ion is 10 to the power minus 7. Similarly, concentration of OH ion is equal 10 to the power minus 7 at 298 Kelvin, and the molar concentration of H2O is 55.5. Therefore, its K is 1.8 into 10 to the power minus 16. Taking negative log of Ka, then we denoted by pKa. It means pKa is inversely proportional to Ka. Means pKa inversely proportional to Ka, a log of Ka. High value of Ka means H plus ion, concentration of H plus ion is more, or ionic species is more than their undissociated form. Higher value of K indicate concentration of ionic species more than their undissociated form, means ionization is high, and the higher value of K means more acidic, and their low value of pK is also more acidic because they are inversely proportional to each other. Taking negative log of the pK, now putting the value of Ka in this equation, log Ka 1.8 into 10 to the power minus 16 in case of water. Therefore, their pKa is 15.74. Now we consider another acid, organic acid, like as acetic acid. In their aqueous solution. It also ionizes in aqueous solution and it gives acetate ion, solvated acetate ion, and solvated H plus ion, or we write hydronium ion also. The Ka of this acid is concentration of acetic acid, acetate ion into concentration of H plus ion upon concentration of acetic acid. Taking negative, the Ka of acetic acid is 1.8 into 10 to the power minus 5 Ka. Taking negative log of Ka means pKa of acetic acid. Then putting this value, the 1.8 into 10 to the power minus 5, taking negative log, it means log 1.8 plus log 10 to the power minus 5. And hence its pKa equals to minus log 1.8 is nearly 0.26, and log 10 to the power minus 5 equals to minus 5 because log 10 equals to 1. Therefore, pKa is 4.6 0.7574, or we can say its pKa is 4.74. Now compare H2O and acetic acid. Its pKa is 15.74 and its pKa is 4.74. It means acetic acid is more acidic, than water, because we know that water is a neutral because equal concentration of H plus ion and OH ion, and the species which carry more H plus ion in their aqueous solution in comparison to water, or we can say their pKa less than water, are acidic and they turn blue litmus paper into red. Now, for relative acidic strength, we consider following factors. After removal of H plus ion, after removal of one H plus ion, the remaining part is known as conjugated base. For example, this conjugated base, and acetate ion is also conjugated base. Acetate ion is also conjugated base. When conjugated base become more stable, then their corresponding acid will be stronger. More stable, then their corresponding acid will be more acidic. And the stability of conjugated base depends upon many factors, in which following are important. Stability of conjugated base depends upon following factor. Main factor, if less value, less negative charge at conjugated base, then more stable. Second, if negative charge carry more electronegative element, then more stable. This factor is important for second period element, because empty d orbital not present in their outermost shell, and hence their negative charge stabilized only by electronegative element, or we can say negative charge present at the more electronegative element, then they are more species, because negative charge according to nature of the species. Solvation of conjugated base, solvation or hydration. Of conjugated base. For example, OH ion is more solvated than acetate ion. Because smaller in size and it is larger in size. But acetate ion become more stable due to resonance. If conjugated base show resonance, and their resonance is synchronized, then they are more stable. Synchronized means equivalent resonance, or we can say all resonating structures have equal stability. Then this resonance is known as synchronized, and it is more effective than unsynchronized. For example, now we consider some important examples about acidic resistance or relative strength. First, we check H2O, HCN, H2O and HCN. H plus ion, OH ion also gives H plus ion and cyanide ion. OH ion is more stable than cyanide ion. First, stability. OH ion is more stable than cyanide because negative charge present at the more electronegative element, and this ion is more solvated. However, the electronegativity of oxygen is nearly comparable to the electronegativity of sp hybridized carbon. Sp 50% S character its electronegativity is comparable to this. But we consider another factor. Bond dissociation energy of OH bond and OC bond. The bond dissociation energy of OH bond is much greater than the carbon-nitrogen bond. Carbon-nitrogen bond. It is nearly 463 kilojoule per mole. And this energy is very less in comparison to carbon-nitrogen. This energy is nearly 413 kilojoule per mole. It means CH bond easily fission, easily breaking in comparison to OH bond. Means H plus ion easily donate in their solution. So now we consider bond energy of carbon and bonded atom. If bond energy is less, then acid becomes stronger. Therefore, HCN is strong acid than H2O. And their solution contain H plus ion. The pKa of HCN is nearly 9.2 and the pKa of water is 15.74. 74 or 75. It means HCN is strong acid. Another example. Taking another example. Bond energy is important factor down the group. For example, HF, HCl, HBr, and HI. Bond energy decrease down the group. Bond energy decreases down the group because the size of halogen increase down the group. Therefore, their orbitals are more diffuse and hence effective overlapping does not take place. And we know that according to BBT, when orbitals which are less diffuse take part in overlapping, then they make a strong bond, and hence HF is a strong bond. Their bond energy is nearly 565 kilojoule per mole. And the bond energy of HF, not the point, the bond energy of HF is 295, only 295 kilojoule per mole. It means HI is a strong acid. However, fluoride, chloride, bromide, and iodide, the electronegativity of fluorine is highest. But according to electronegativity stability, but presence of empty d orbital, their negative charge disperse in their empty orbitals, as well as less bond energy down the group. Therefore, acidic strength increase down the group. This factor is very, very important when much difference in the bond energy, and or we can say it is important factor down the group. For example, similarly, H2O, H2S, chalcogens, H2O, H2S, H2AC, and H2TE. The acidic strength increase down the group. Like as HX, because decrease bond energy as well as their negative charge disperse. Negative charge of conjugated base disperse in their empty orbital, and such type empty orbitals are not present in the element of second period, and hence acidic strength increase down the group. Now another question. Conjugated base are also stabilized by resonance. For example, we consider three acids, namely H2CO3 carbonic acid, namely acetic acid, namely sulfurous acid H2SO3, namely H2SO4 sulfuric acid, and namely perchloric acid HClO4, and namely HI. Then and also HF. After removal of H plus ion, their conjugated base H bicarbonate ion, it has two resonating structures in which negative charge disperse at the oxygen, both oxygen. In case of acetic acid, its conjugated base also so resonance, and in which negative charge also delocalize at two oxygens. In sulfurous acid, their conjugated base also resonance and their negative charge disperse at two oxygens. In H2SO4 sulfuric acid, the bisulfate ion also exhibit resonance and their negative charge disperse at 3 oxygen, equivalently at 3 oxygen. In perchloric acid, after removal of H plus ion, their negative charge disperse at 4 oxygens, equivalently 4 oxygens. And in case of HI, no dispersion of negative charge but less bond energy. In case of HF, no dispersion of negative charge but presence of empty but it is high electronegative element. Then it means perchloric acid. Has more stable conjugated base, most stable conjugated base due to resonance. Therefore, it is a strong acid. However, some references tell HI have comparable acidic strength of HClO4 due to less bond energy and their pKa. The pKa of both acids are nearly -10. Or we know that less value of pKa means strong acid. Therefore, HClO4 and HI have comparable acidic strength, or we can say nearly equal acidic strengths. This stabilized due to resonance synchronized, and this stabilized due to negative charge in their empty orbital as well as less bond energy. In case of fluoride, negative charge is not delocalized, but due to high electronegative element. Fluorine have highest electronegativity among all known elements. Therefore, negative charge disperse. Therefore, negative charge stabilize as well as smallest ion and hence higher solvation energy. Higher solvation energy of fluoride ion. Therefore, it is also stronger. Now, we consider these acids. Bicarbonate ion, acetate ion, and sulfurate ion. Bicarbonate ion to resonating structure, but this oxygen destabilize the resonating structures. No lone pair. Here lone pair also, but sulfur is third period element. Therefore, this effect is negligible because larger size of third period element and hence repulsion between these oxygens is less in comparison to bicarbonate ion. And hence acidic strength H2SO4 is another strong acid because negative charge disperse in their 3 at oxygens. The bicarbonate ion pKa, particularly pKa1, is 6.38. In acetate ion, pKa is nearly 4.74. In bisulfate ion, pKa in sulfurous acid. In sulfurous acid, is it also a strong acid? It is also a strong acid. However, it is weak acid in comparison to sulfuric acid. Its pKa is nearly 1.9. In sulfuric acid, it is a strong acid and its pKa is nearly 0.3. pKa means a strong acid. It is a strong acid, pKa this. And in case of HF, its pKa is also nearly 2 point something, 2.3.5. It means HF is weak acid in comparison to sulfuric acid. Very weak acid. This pKa is nearly 2. Is nearly 2.3 or 2, nearly 2. Now we consider another example of organic acids. For example, we consider phenol and carbonic acid, H2CO3. The phenate ion have unsynchronized resonance because during the resonance their negative charge disperse at the carbon. Therefore, the unsynchronized resonance is not effective as in synchronized resonance. But in case of bicarbonate ion, the resonance is synchronized because negative charge disperse only at oxygen. And when two oxygens take part in resonance and carry negative charge, then bicarbonate ion is more stable than this. It means bicarbonic acid, H2CO3, carbonic acid is more acidic than phenol. Its pKa is nearly 10 and its pKa 1, particularly 1 is important, is nearly 6.38. 6.38. It means phenol is less acidic than bicarbonic acid. Now we consider sulfonic acid, RSO3H. Its conjugated base is most stable, like as inorganic acid, H2SO4 is more stable, like as inorganic acid, because their negative charge disperse at 3 oxygens, and oxygens are more electronegative element. Therefore, its Ka, pKa is also greater, like as -2, means it is also a strong acid. So now we check relative strength of phenol, carboxylic acid, and sulfonic acid. Nearly 1 lakh time difference in their Ka. K of phenol is nearly 10 to the power -10. K of carboxylic acid in the range of 10 to the power -5, and K of sulfonic acid is 1 or more. 1 or more means their relative acidic strength is very much difference. Another question, we check H2O and H2S, H2 and H2S, OH ion and HS ion. First, we check less bond energy of HS as well as their negative charge of bisulfide ion disperse in their empty orbital. Therefore, H2O is strong acid than H2S is strong acid than H2O. Their pKa is nearly 15.74 and pKa 1, because it is diprotic acid, is nearly 7, means strong acid. The Ka of alcohols, pK of alcohol, also check the K of alcohols. Alkanoate ion is less stable than hydroxide ion. Stability region, because due to plus I effect of alkyl group, their negative charge, higher value of negative charge. Due to larger size of alkoxide ion than OH, they are less solvated or less hydrated. It means water is more acidic than alcohol. But exceptionally methanol is slightly more acidic than water. Their pKa is 15.5, pK of water is 15.75, 7475, and pK of alcohols nearly 16. The region of methoxide ion, the methoxide ion is slightly more stable than hydroxide ion, because the electronegativity of carbon is greater than the electronegativity of this hydrogen. Electronegativity of carbon is greater than the electronegativity of this hydrogen. It means more negative charge at oxygen, in hydroxide ion than methoxide ion. It is the reason. However, some other alkoxide ion, plus I effect is more dominant. Therefore, they are less stable. Stability order: methoxide ion, hydroxide, and other alkoxide ion. Now we consider some effect of substituent on the acidic basic strength of carboxylic acids, aromatic carboxylic acid. For example, benzoic acid and orthotoluic acid. We check another effect, steric inhibition of resonance. When bulky group or atom present at the ortho position, then they repel to each other, or we can say this conjugated base have less affinity toward the proton, means steric inhibition of protonation or resonance. Steric inhibition of protonation when bulky group present at the ortho position of benzoic acid, then due to steric inhibition of protonation, higher concentration of H plus ion in their solution, and hence ortho substituted benzoic acid are more acidic than benzoic acid due to SIP, or it is also known as ortho effect shortly. It is also known as ortho effect. For this effect, bulky group present at the ortho position. Now we discuss some questions regarding to acidic strength. Question number first. Correct order of the acidity of following compound. First H2S, H2O, HCN, carbonic acid, phenol, HF, and acetic acid. First, we check stability of conjugated base. Bisulfite ion, OH ion, cyanide ion, bicarbonate ion, phenate ion, fluoride ion, and acetate ion. First, among all conjugated base, fluorine has highest electronegativity, and it is second period element. Highest electronegativity among all known element, and negative charge present at according to their nature, as well as smallest anion among these. Therefore more solvated, and hence HF is strongest acid in given question. Now we check resonance in which synchronized two, a bicarbonate ion and acetate ion have synchronized resonance, but in case of bicarbonate ion, carbon, its central atom is carbon, and the lone pair of OH group repel to each other. Therefore acetate ion is more stable than bicarbonate ion, and then acetic acid is stronger, and then carbonic acid. In case of HCN, cyanide ion is more stable due to negative charge present at the sp hybridized carbon atom, sp hybridization carbon. But in case of bisulfide ion, their negative charge disperse in empty orbital, as well as the bond energy of carbon hydrogen is greater than the bond energy of carbon and sulfur, because sulfur is third period element. Their orbitals are more diffuse, and hence effective overlapping does not take place, and hence H2S is strong acid than HCN. The pKa of H2S is greater, nearly 7, and the pKa of HCN is 9.2. It means H2S is strong acid, then H2S, then HCN, then phenol, because resonance also there, but resonating structures have unsynchronized. It means phenol is less acidic than acetic acid, then as well as carbonic acid, but it is strong acid than water. Water is weak acid in given question. Question number second. How many compound among the following which gives Brix effervescence with sodium carbonate? When acid react with sodium bicarbonate, then they gives carbonic acid. If carbonic acid is formed, then it evolve Brix effervescence of CO2, and the reaction will be forward if given acid is strong than carbonic acid. It means when given acid is stronger than carbonic acid, then such acids react with sodium bicarbonate then make H2CO3, or they gives Briggs effervescence of CO2 because the carbonic acid dissociate into water and CO2. Now check. Thiophenol is weak acid than carbonic acid. Thiophenol is weak acid than carbonic acid because in bicarbonate ion two resonating structure and negative charge present at the two oxygen, but in thiophenol negative charge present at the sulfur as well as carbon due to resonance. Therefore bicarbonate is more stable than thiophenol. Therefore this compound is not evolved. In case of sulfonic acid, strong acid, then it evolved. For example, understand some reaction of phenol of benzene sulfonic acid with sodium bicarbonate. This is the benzene sulfonic acid plus sodium bicarbonate. Then sodium salt of benzene sulfonic acid and H2CO3. Carbonic acid. Now we check acidic strength of benzene sulfonic acid and carbonic acid. We know that benzene sulfonic acid is strong acid, then carbonic acid it is weak acid, and we know that stronger acid are mainly exist in their ionized form, or we can say strong acid are easily deprotonated. It means reaction shift to forward direction, and reaction shift to forward direction make carbonic acid and evolve CO2. It is not an acid. It is also strong acid than carbonic acid. When second and fourth position, or we can say ortho and para position of phenol occupy with strong electron withdrawing group, then they are strong acid, then become stronger acid than carbonic, and hence also evolve CO2. Phenol does not evolve because phenol is weak acid than carbonic acid. Acetic acid is also strong because two resonating structure as well as negative charge disperse at oxygen, but no repulsion between carbon and carbon of methyl. H2S is weak acid, not evolve. Sulfonic acid evolve. HF also evolve. Carbon HCN and carbonic acid. HCN is also weak acid because carbon no resonance in conjugated base, but carbonic acid two resonating structures are there. Therefore HCN is weak acid. Than carbonic acid. Notice its pKa is nearly 9.2 and the pKa of carbonic acid is 6.38. It means carbonic acid is stronger acid than HCN. Therefore it does not evolve. Alcohol are not evolved, and hence 1, 2, 3, 4, 5 and 6 acids evolve CO2 or Briggs effervescence with sodium bicarbonate. Question next. Correct order of the acidity. First, in compound first and second, SIP, steric inhibition of protonation is takes place, as well as their conjugated base also make H bonding, and hence more stable. First more stable, then second conjugated base, then this. And now in consider question number third and fourth. At para position, the due to plus M effect of OH group it raise electron density at the ortho and para. Therefore their conjugated base become more stable, and but OH group present at the meta position, its minus I effect is dominant, and hence its acidic strength is greater than para. Means para hydroxybenzoic acid is weak acid, and hence the correct order of is given is the correct acidic strength. Now question number next. First, correct order of the acidic strength of following: carboxylic acid, NH3 positive and NH3 positive XY. This after removal of H plus ion, resonance present in the carboxylate ion, but no resonance in NH3 positive. Therefore carboxylic acid is more acidic, means X is more acidic, and it also exhibit minus I effect. Minus I effect is distance dependent. Therefore, Z is more acidic than Y because minus I effect group are far away from the NH3 group. Therefore, acidic strength is X, Z and Y. D option. Next, question number next. It is also important question. It is also important. Which of the following acid has higher dissociation constant? Check the option. This is the benzoic acid. First, benzoic acid is weak acidic, then formic acid. Reason? Because the electron density of benzene ring and electron density of carboxylate group are more close, like as OH ion, Therefore, they destabilize the resonating structure. But in case of formate ion, resonating structure are synchronized and no electronic repulsion. Therefore, formate ion is more stable. It means formic acid is more acidic than benzoic acid. Now we consider 3-fluoropropanoic acid and 3-bromopropanoic acid, and the halogen have minus I effect and they increase the acidic strength. But when the distance of halogen from carboxylate ion is 3 or more carbon, then this effect is negligible, or we can say their acidic strength is less than formic acid. It means formic acid is stronger acid among these. Therefore, it has higher dissociation constant. Understand the value of formic 3-fluoropropanoic acid and bromo. However, when strong electron withdrawing group like as nitro present at the third position, when strong electron withdrawing group present at like as nitro, cyanide, etc. present at the third position, then their acidic strength becomes stronger than formic acid. But in given question, only formic acid is strong acid. Therefore, it has higher dissociation constant. Means their Ka is highest. Question next. Rank the compound. Order of decreasing order of acidic strength. After removal of H plus ion, the negative charge take part in resonance. After removal of H plus ion, no conjugation in their negative charge. After removal of H plus ion, the negative charge take part in resonance with CO first and CO fourth, adjacent CO. Therefore, most extended resonance in third, and hence more acidic than in first, and in third, second is last, because their negative charge conjugated base, not so resonance. Question next. Which one of the following is most acidic? Acidic means after removal of H plus ion. After removal of H plus ion, we check stability of conjugated base. After removal of H plus ion, this species is anti-aromatic. Anti-aromatic is least stable. Therefore, acidic strength is less. After removal of H plus ion, the remaining species conjugated base become aromatic, and hence most stable. After removal of H plus ion, the remaining species is conjugated base is also anti-aromatic. And after removal of H plus ion, it forms allylic cation, but allylic cation is less stable than aromatic species. Therefore, most acidic hydrogen present in group present in B option. Very important question. Correct order of the pK of following compound. After removal compound, we consider compound first. After removal of H plus ion, its conjugated base is following. After removal of H plus ion, anywhere after removal of H plus ion, its conjugated base is following. And due to resonance, it is an aromatic species. Or we can say, if aromatic character are present in their conjugated base, then they are most stable. And hence their acidic is stronger acid. And we know that stronger acid has less value of pK. It means lowest pK of compound first. We check compound second. After removal of H plus ion, their conjugated base. After removal of H plus ion, their conjugated base also exhibit resonance and carry aromatic character. Delocalization of this, carry aromatic character. Positive, this. ठीक है, aromatic character. But carbon hydrogen carbon-hydrogen bond is less acidic than OH bond. Carbon-hydrogen bond is less acidic than OH bond. OH bond. Therefore, compound first is more acidic than compound second. In compound third, no resonance is there. It means it is least acidic. No resonance is there in their conjugated base. And hence it is less acidic. And means their pK is highest in third, then somewhat lower than second, and lowest in case of first. Question number 9. Question 10. In which of the following pair second compound is weak acid? In case of first, compound first is more acidic than second. Reason? Because this show minus M effect, and we know that minus M effect make stabilized phenate ion due to resonance effect. Means first one is more acidic, therefore second one is weak acid. In case of thiophenol and phenol, sulfur carry empty orbital and their negative charge disperse in their empty orbital, means first is more acidic. In case of this compound, first is also more stable because due to plus H effect of methyl group, they destabilize the phenate ion. First is more acidic. In case of fourth, orthotoluic acid is more acidic than benzoic acid because SIP, because steric inhibition of protonation due to bulky group present at the ortho position, means their solution carry high concentration of H plus ion and are more acidic. In case of compound 6, it is cyclic compound, benzoic cyclohexane carboxylic acid and 2-methyl cyclohexane carboxylic acid. Second one is less acidic due to plus I effect, because in which the carbon has sp3 hybridization, and due to larger bond distance, no SIP type effect. In which in toluic acid the carbon have sp2 hybridization, and we know that sp2 hybridized carbon have short bond length, means their groups are more close to each other and they repel to each other, and as SIP is significant value. Therefore, in fifth, first is more acidic than second. In case of acetaldehyde and acetone, acetaldehyde is more acidic because its conjugated base become more stable. Due to resonance in which no plus I effect. In case of conjugated base of acetone is slightly less acidic due to their plus I effect of alkyl, and hence acetaldehyde is more acidic than acetone. Therefore, all are correct. Okay, and there are some questions about relative acidic strength of organic as well as inorganic acids. Okay, bye.